Okay, so let's remember what we're talking about. Somebody tell me what we were talking about. What is the topic? Generally, or precisely? Yes? Inner product. So yeah, that's the topic of the whole chapter. Right, inner product, which is a generalization of dot product, right? But what have we been doing more recently? What did we do last class? What was the topic last class? Anybody remember? No?
Orthogonal complements.
Orthogonal complements, right? So with a dot product, you have a notion of orthogonality, right? We talked about things being perpendicular to each other. And so we have this thing called the orthogonal complement. So the orthogonal complement of a subspace of R. Right? So you have S a subspace of Rn, and then you have this thing S perp, right? The orthogonal complement. Remember what the orthogonal complement is. What is it? It is, what's the orthogonal complement of a subspace? Montana?
You standard vectors such that they're all orthogonal to all the ones in the
Okay, leave out the word span maybe, and that's good enough. You say it is all the vectors, right? It's all the vectors in Rn, right? Any vector in Rn such that x is perpendicular to every element in S, right? All the vectors on Rn that are perpendicular to all the elements in S. It's all vectors in Rn that are orthogonal to all vectors in S. Right? So that's the orthogonal complement, right? Everything that is orthogonal to everything in your subspace, right? And then we proved a bunch of facts last time. One was that the dimension of the subspace plus the dimension of its orthogonal complement had to add up to the dimension of the ambient space, right? The dimension of the Rn that they're living inside, right? And we also showed that if B1 to BR was a basis of S, and BR plus 1 to Bn is a basis of S perp, then the union B1 to Bn is a basis of Rn. Okay. So those were the two facts that we talked about last time. Okay. Those are two of the things we said about orthogonal complements last time. Okay. So today we're going to remember there are two ideas in this section. One is orthogonal complements. The other is this thing called direct sum. Okay. So now today we're going to talk about this thing called direct sum. And this seems like kind of an abstract idea, but it turns out to be extremely useful, and in fact useful in practical applications. So next class we'll be talking about the method of least squares, which is sort of like maybe the beginning of machine learning, one entry point into machine learning, and this method of least squares relies on the stuff that we do in this class, including this notion of direct sum. Okay. The method of least squares was introduced by Newton. By Gauss. By the great mathematician Gauss. And the story is that, I mean, this is history, not a story, but
It's the same thing, right?
I guess. Yeah, so yeah, I'll give some rough story that is roughly true. Okay. The story is that there was an asteroid approaching the Earth, Ceres, I think. Is that right? No, Ceres.
Yeah.
Ceres. It's in your book, yeah. Just read the book. Anyway, so there's an asteroid Ceres approaching the Earth. Some astronomers try to say where it's going to appear. They say, we think it's on this date it's going to appear here next, but Gauss says, no, it's going to appear here. And Gauss turns out to be right. And this cements his reputation as the top astronomer of the day. Right. And the method that he used was method of the least squares that we'll do next time.
So he invented it?
Yeah. Like basically everything was invented by Gauss.
Yeah.
Okay. So direct sums. It's kind of a strange notion though. So let's be careful with it. So you have two subspaces, U and V, subspaces of W, a vector space. Here. We say that W equals U direct sum V. Okay, we say that W equals U direct sum V. In other words, W is the direct sum of U and V. If every every vector in W can be uniquely expressed as U plus V for some U in U and some V in V. Every W and W can be uniquely expressed. So so what this says is that everybody in W can be expressed as a sum, right? You can break up, it has like a decomposition, right? Every vector in W can be decomposed into two parts, one of which is in U and the other of which is in V, and that can only be done in one way. Okay, if that's the case, we say that W is the direct sum of U and V. And we write this funny addition symbol. So for example, right, if I take my U to be the span of 1, 0, 0, and my V to be the span of 0, 1, 0, and 0, 0, 1, right? The x-axis and the yz plane, right? Then you see that if I have, so here is my U, here is my V, right? You see that if I have any vector, so if I have some vector W in R3, then I can break it up into two parts, right? I can break it up into somebody in V, somebody in V, and somebody in U, right? Okay, somebody in U, right? So anybody in R3 can be expressed as somebody in V plus somebody in U, and there's only one way to do it, right? You see what I have to do? I take the orthogonal projection here, right? And I use that. Right? That guy is my U, and the thing that you project onto here is V. right? Okay, so here R3 is U plus U direct sum V. Yeah, yeah.
So are U and V orthogonal complements?
They actually are. So yeah, so secretly, and I wasn't going to say it yet, but you revealed it. Yeah. Notice that actually this V is the orthogonal complement of U. Now I'm going to give a non-example. Let U prime be the span of 1, 0, 0, and 0, 1, 0. Right, so this is the xy plane, and V as before. Okay, so then I get, so here's my U, right, and my U goes this way, and my V goes this way. My V goes this way, right? Okay, and now you see that if I take my W, that same W, I have actually multiple ways of breaking it up into something in U and something in V, right? So I have the way that I had before, right? I can break it up U, V, like that, but I can also project this way, say, right? I get something in U, so I get this U prime here, and I get this V prime, right? I get this V prime, right? So there's actually multiple, it's true, everybody can be expressed, right? So certainly it's true that R3 is the sum of these subspaces, right? R3 is the sum of these subspaces, right? Everybody in R3 can be expressed as somebody in U plus somebody in V, but it's not the direct sum. Direct sum means that there's only one way to do it. And here we see that there's multiple ways of doing it. So R3 is not the direct sum. So yeah, Abba.
Does U always have to be an orthogonal complement of V for W to be a direct sum?
What do you think?
Yes.
What do you think? Can anybody see a way of decomposing R3 into two subspaces that are not orthogonal to each other, and yet the way you could? There's only one way of expressing elements as sums. Just move this, just angle this a little bit, right? If you take your V and rotate it, give it a little bit of an angle, then still it's going to be a direct sum, right? But they're not orthogonal complements to each other because they're not orthogonal, right? They're not orthogonal. Okay, so no, it doesn't have to be the case that they're always. It's not true that if you're a direct sum, then these guys are orthogonal complements of each other.
The orthogonal complement is a direct sum.
So that's what we're about to prove. So here's the theorem. If let S be a subspace of Rn, then Rn can be broken up into the direct sum of the orthogonal complement of S with S. Okay, so you have two parts of the proof. You need to show two things. One, that we need to show one, that every W in Rn can be expressed as U plus V, where U is in S and V is in S perp. And two, that this decomposition is unique. i.e., if W equals U prime plus V prime also, then U equals U prime and V equals U. Okay. Okay, so I want you to try to figure out this first one. The first one actually is not hard. So why is it true that if you have a subspace, then everybody in R, if you have a subspace of Rn, then everybody in Rn can be expressed as the sum of something in S and something in S perp. Okay. Why is that true? This is actually a consequence of something you know about orthogonal complements. Okay, so think about it for a minute and then talk to somebody new. Okay, talk to somebody nearby, please. Okay, so would somebody like to say why everybody in Rn can be expressed as something in S and something plus something in S perp? Trevor?
So don't S and S perp have their own bases?
Yes, yes, exactly. So you say, well, look, we know that, so take two bases, right? B1 dBr be a basis of S, say, and Br plus 1 dBn be a basis of S perp. Right? Then we've got that, what we did last time, B1 dBn is a basis of Rn. So,
Well, if U comes from S and V comes from S perp, then can't you have a linear combination of them to equal W Rn?
you're sort of saying it backwards, right? You want to show that W can be expressed as something in S plus something in S perp. You don't start off with U and V to begin with. You want to show that U and V exist. So how do you show that you can write this thing as something in U plus something in V? You basically got it.
I don't know how to word it.
Okay, so you say, well, look, W, right? This is a basis of Rn, so W can be written as as a linear combination of these guys.
Right.
Right? So you say W is C1 B1 plus C2 B2 plus CR BR plus CR plus 1 BR plus 1 plus CN BN. Right? And you say, well, look, this is something in U, something in S, and something in S perp. Right? This thing is in S, and this thing is in S perp. Right? So yeah, W can be expressed as something in S plus something in S perp. Okay, so that first part is done. Everybody in Rn can be expressed, this will be your U and that will be your V. Right? Everybody in Rn can be expressed as this sort of sum. Okay, now, so that's part one. Part two, right, you want to show uniqueness, right? So if, say, W equals U plus V, and W also equals U prime plus V prime, where the U's are in S and the V's are in S perp. Okay. We want to show that U minus U prime is 0, and that V minus V prime is 0. So, Ada?
Isn't like the extra question on the midterm where you have like third basis and they should be able to express LVD uniquely?
Not exactly, not exactly. Because this is, within one space, you're wondering if within that one space, there's multiple ways of doing it. So it's not exact. I don't think it's exactly the same.
But if B1 to BR is the basis of S, that means for every vector in that, there's a unique expression with that, like, because of that basis. And couldn't we use that, like, I don't know.
No, maybe. Let me think, right? So you're saying, well, look, this is a basis, right? And it's linearly independent, right? So you know that
Unique expression.
the only way to express this guy as a linear combination of these guys is like this. So
Any other expression if U prime like have the same extended aspects?
something seems kind of funny about that to me. So you say, well, look, no, I think that works. I think that works. You would say, well, look, right. So you'd say, well, suppose that U is C1 B1 plus CRBR, right? And V is CR plus 1 V R plus 1 up to CN BN, right? Right? And suppose that U prime is C1 prime V1 prime plus CR prime BR, and V prime is CR plus 1 prime BR plus 1 plus CN prime BN. Right?
Then we can subtract.
And then you would say, well, look, then, and W, right? W equals both of those things. Right? It equals U plus V, but it also equals U prime plus V prime, right? Right. let me think about it. Something seems a little strange to me. So let me just explain it the way I wanted to explain it and think about it. Okay. So if this happened, you'd say, well, what do you notice about u minus u prime? What can you say about u minus u prime here? If u plus v equals u prime plus v prime, then what's u minus u prime?
Zero.
Zero. Why?
Because of the same. Well, they're supposed to be the same. Correct.
That's what we're trying to show. We're trying to show that that this is going to be zero. Okay, so but just looking at this thing here, u plus v equals u prime plus v prime. So u minus u prime is going to be, okay, if u plus v equals u prime plus v prime, then we know that u minus u prime equals what?
V prime minus.
V prime minus v. Okay, and so why is that equal to zero, right? We're hoping that that equals zero. Why? It actually does equal to zero. Why? Well, where is this thing? This thing lies in S, and this thing lies in S perp, right? So you have something that lies in S, and it also lies in S perp, and so it's got to be zero, right? Right, since anything that lies in S and S perp must be the zero vector. It's okay. Okay, so that gives us, that's the end of the proof. That gives us this fact that anytime you have a subspace, then subspace of Rn, you can look at its orthogonal complement, and Rn will be expressible as the direct sum of that subspace plus its orthogonal complement. Is that video away? Mariah? Not sure?
No, yeah, makes sense.
Yeah, okay. Okay, so a couple more things. So next is the theorem about S perp. Okay. The orthogonal complement of the orthogonal complement. What do you think I'm going to write here? The orthogonal complement of the orthogonal complement
Yes.
is S again. Right? That sort of makes intuitive sense, right? If you look at the guys who are perpendicular, all the guys who are perpendicular in the set of all the guys who are perpendicular to S, then it must be S itself. Okay, so let S be a subspace of Rn. Right. Then the orthogonal complement of the orthogonal complement equals S. So we're going to prove this in two parts. First, we're going to show that if you're in S, then you're in S perp perp, and we're going to show if you're in S perp perp, then you're contained in S. So we'll show mutual inclusions. Okay. So first thing we need to show is that we want to show that if you have some vector in S, then V must be in S perp perp. So think about that for 15 seconds. What does that mean? You want to show that if you're in S, then you're perpendicular to the guys who are perpendicular to S. Right? Of course you are, right? Of course you're perpendicular to the guys who are perpendicular to S, right? Because you're in S, right? If you're in S, you're perpendicular to the guys who are perpendicular to the guys in S, right? So that's obvious. Okay, so this is actually obvious, right? You say, well, look, right? if V is an S, then certainly V is perpendicular to anybody in S perp, right? But that means that you are in the orthogonal complement of S perp. We need to show the opposite inclusion. We need to show the opposite inclusion. So say, let X be in S perp. Okay. We want to show that X must then be in S. Right? We're trying to show now that the left side is included in the right side. Last time we showed that the right side is included in the left. And this direction turns out to be a little bit trickier. And what you use is actually the direct sum that we just proved. You say, okay, well, right? We know that Rn can be written as S plus S perp. S direct sum S perp. Okay. So X can be written as U plus V, where U is in S and V in S perp. Right? Now consider the dot product of V against X. What's the dot product of V against X? Well, X, remember, was in S perp perp. V is in S perp. So it's 0. Right? Right? So you've got something in S perp perp, you've got something in S perp. They're perpendicular to each other. Okay? Okay, but you notice I'm going to replace this X with U plus V. You get V transpose against U plus V equals 0. Right? But this is V transpose U plus V transpose V. Right? But what's V transpose U? What's the dot product against V of V against U? 0 also. Right? Because U is in S and V is in S perp. Right? U is in S, V is in S perp, so the dot product is 0. So this is 0. But that tells you that V transpose V is 0, right? In other words, that the magnitude of V squared is 0. Right? So that tells you that V is 0. Right? V must be the 0 vector, because its magnitude is 0. Okay? But going back here, right, X was U plus V. Right? So that means X is just U. Right? X is U plus 0. Right? In other words, X is something in S. Right? X equals U, but U is in S. Right? So we see that anybody in S perp perp lies in S. Anybody lying in S perp perp lies in S. Okay, and so we see that those are the same thing, right? S, the orthogonal complement with the orthogonal complement is just the set itself. Okay, any questions? Any questions? Okay. So,
Zero again?
why is v 0? Because we see that we took the dot product of v against x and saw that that's the same thing as the magnitude of v squared. But the magnitude of v squared is 0 then,
Oh, okay, so you said.
right? So
Okay.
the only vector whose magnitude is 0 is the 0 vector. Okay. Okay, is everybody all right? Okay, one last thing in this section that sort of brings together a lot of the ideas that we've been doing in this section. Okay, so clarifying the relation between the row space and column space. Clarifying the relation between the row space and the column space. Okay, so let's recall that way back when we talked about the rank, we noticed that the dimension of the row space of A and that of the column space were the same, right? And that's why we called the rank the dimension of the row space, because the dimension of the column space is the same thing. Okay. Now let me write this in more sophisticated notation. Right? Remember, the column space is the range of A. Right? The column space is the range of A. Right? You multiply by A. Everything that comes out is the linear combinations of the columns of A. Right? So that's the column space is the range of A. The row space is the range of A transpose. Okay, so what we were saying back then is that the range of A transpose and the range of A both have the same dimension. Okay, so let's say, okay, so let's think. So say that A is an n by n matrix. Okay, so then T sub A goes from where to where? T sub A. N to M, right? So from Rn to Rm. Right? From Rn to Rm, and notice that the range of A transpose. Okay, so A transpose is a n by m matrix, right? The range of A transpose is where? The range of A transpose Rn, right, is in Rn. Is in Rn, right, is in here. Right, because just as you so quickly said a second ago, right, if you're looking at the range of T transpose, this is going to go from Rn to Rn, Rn to Rn, right? So the range of A transpose is going to be in Rn. Right? Okay. I hope nobody's getting lost here. This is just, we're just keeping track of. We're just writing these things down for convenience. Okay. Okay, so notice, I'll write it again. The range of A transpose is contained in Rn, and so if we take Rn, we can break it up into range of A transpose, direct sum, range of A transpose per the orthogonal complement of the range of A transpose. Everybody all right? Okay. But what's the range of A transpose's orthogonal complement? We actually know something about this thing, right? The orthogonal complement of the range of A transpose is by the fundamental subspaces theorem.
Null space of A.
The null space of A. Right? So this is the null space of A. So Rn can be broken up into the range of A transpose plus the null space of A. Okay. Okay. So. Okay. So now. Consider the map T sub A going from Rn to Rm. Consider the map going from T sub A going from Rn to Rm. Okay. T sub A is going to map onto the range of A. So I'm just going to replace this by the range of A. Right? This thing lives inside of Rn. Right? T sub A is going to map onto the range of A inside of Rn. Right? So we've got T going from Rn to the range of A. So consider this thing. Okay. So let me just write like this. Rn. So I'm going to replace this thing by the range of A. Replace this thing by the range of A. And I'm going to replace this Rn by range of A transpose plus the null space of A. Direct sum of the null space of A. Right? So this was Rn, this was Rm, right? But I'm going to replace it by these things, right? Because this is equal to this, and this is inside there. Okay, so, T sub A. Okay. So now notice this n sub A, this n of the null space of A, when you look at stuff that when A acts on the null space of A, it just goes to 0, right? So this null space of A doesn't contribute anything. So I'm just gonna exit off, right? Right. It's true, right? If we look at how A acts on Rn, well, Rn is the range of A transpose plus the null space of A, but the null space of A just gets mapped to 0 over here, right? So this null space of A actually doesn't contribute anything. I'm just going to leave it off. Okay. So so in fact, we think of T of A going from here to here. Okay. Okay. So our claim is actually that T sub A going from RAT to the range of A is actually an isomorphism. Okay. In other words, that the column space and the row space are actually isomorphic to each other. Okay. That's why they have the same. That's why they have the same dimension. There's actually an isomorphism between them. Okay. And the isomorphism is just, multiply by A. Okay. So we need to show two things. We need to show that T sub A is onto, and that T sub A is 1-to-1. Okay. So the first part, you think, well, look, if I look at T sub A going from Rn onto the range of A, well, this is onto, right? This is onto, right? Because if you look at, the range of A is the collection of all outputs, right? Well, these are all the inputs, right? So if I feed T sub A all of Rn, I'm going to get all the outputs, right? So this is definitely onto, right? Because Ra is just the stuff that comes out of this, right? So this is definitely onto. Montana.
I'll ask you after.
Okay. So, right, what does it mean to be onto? It means that everything here can be